So the last talk was well placed because you were talking about Heisenbugs and systematic testing to find strange behaviors, and also why, or the question of whether weak memory matters. I'm going to put forward a different position, which is actually that these things do matter. Models do matter in particular. The title is slightly different, as was what was on the website, but the content is the same, just last-minute review things. So I've been developing techniques to find concurrency bugs in C++ compilers using relaxed memory models. Now, briefly, as some of you will know, a concurrency bug will arise when the compiled program behavior under some hardware implementation or model therein is not a behavior of the source program under some reference semantics, such as C or C++. In practice, outcome of execution that you don't expect, which is not otherwise allowed by the C model. Now, it's been a decade since the C and C++ models were introduced, so you might reasonably expect that most of the bugs have been found, or at least most of the testing's been done. There's been a lot of eyes on this, both in academia and in industry, so that's a reasonable assumption. However, I'm here to say that actually that might not be the case. Now, the thing I'm claiming here is that hardware implementations are increasingly exploiting the allowed behaviors of relaxed memory models. So what I mean by this is hardware implementers, they want to get as much performance out of their chips as they can, so they're increasingly using the allowed relaxations of these relaxed architecture models. This claim isn't surprising, but the implications of it might be a little more surprising. In summary, more relaxed hardware means more potential outcomes of a concurrent program, and that potentially means there are going to be more compiler bugs which may not have been observed under prior techniques and prior work. So I'm going to be exploring that today. In particular, I'm going to be exploring three implications of that claim using a running example of a bug I found in LLVM a few months ago. It's been reported. I believe it's going to be fixed by some engineers soon. The 3 points today that hopefully will be a bit controversial and stir up some interesting chats. We're going to need to update our compilers and our testing tools to reflect architectural relaxations. We might need to have another look at our test generators to make sure we're covering all the edge cases. The last talk mentioned Heisenbugs. This is one of them. And we may need to revisit assumptions regarding the soundness of compiler optimizations as hardware is more relaxed. So I'll be going over those one by one using the running example here. So this is a litmus test. For those of you who don't know, litmus tests have concurrent threads of execution, P0, P1, that read and write to shared memory using shared locations X and Y, using atomic loads and stores. The order in which instructions are executed on each thread will be synchronized by fences and control flow, and so on. So if you run this test from some fixed initial states where X and Y is 0, the C++ model permits that this program will end in one of those three outcomes of execution on the right. Now, quickly, that syntax means thread P1, local variable R0, will have the final value 0, and shared location Y will have the value 1. This is a bit of a terse syntax, but essentially each line is an outcome of an execution. If you compile this to target ARM v8.2a with the large systems extension enabled, you will observe one more outcome. That is not allowed by the C model, and yeah, that is what I call a compiler bug. A compiled program behavior that is not allowed by the source semantics. This is the running example. I'm not going to go into detail on now why this is a bug, but you'll understand by the end of the talk, hopefully, the details of why this is a problem. So, back to my claim. Hardware is increasingly exploiting relaxed models. The first implication of this claim is that we're going to need to update our compilers and our testing tools. So this test, I didn't actually find this compiler bug until herd tools was updated. That's the basis of all the checking I've been using. And herd tools was updated to reflect the architectural intent of the ARM architecture specification, which is the official source of the allowed behaviors of the ARM architecture. Now, the ARM architecture reference does allow this reordering that gives rise to this buggy behavior, but if you were to run testing on old hardware that doesn't implement 8.2a, you wouldn't necessarily observe this outcome of execution and hence this bug. So yeah, consequently, any compiler testing tools that rely on old hardware might not observe this bug as well. The conclusion I bring from this is we need to parameterize our testing over source and architecture models so that we can find compiler bugs, but also bugs in the testing tools themselves, such as herd. And this is drawing back to a previous point about the need for systematic testing of atomics. Cool. That's what I'm doing. In upcoming work in CGO 2024, Lee and I are presenting a tool called Teleshat, which takes a concurrent C or C++ litmus test, compiles it, and simulates the allowed behavior of source and architecture, source and compiled programs under the source and compiled programs respectively. We found quite a few compiler bugs. We found a few toolchain bugs in herds, and as far as I know, this is the first tool of its kind to be deployed in industry. It's the first one to be deployed in automated regression testing for ARM compiler. Yeah, so we need to parameterize testing over source and architecture models, or something as close as we can get to the ground truth. The second implication of this claim here is that we might need to also update our test generators. So this example, some keen eyes amongst you will have realized this is a special variant of the message passing litmus test. P0 does two stores to x and y, and P1 does a read modify write of y followed by a load of x. Now, conventionally in a message passing test, you will store the value written by the exchange into some local variable R1, and then you'll check reordering with R1 with respect to R0 in order to see if message passing has been reordered. As far as I know, the state-of-the-art test generators will not generate this test on the right. I hand wrote this thing, and it took me a lot of thinking to do so. And so the conclusion I draw from this is, yeah, we need to have another look at our test generators in order to do a bit more systematic testing of the compilation of atomics. I realize this is an edge case litmus test where we're not considering the value of a read, but nevertheless it induces a bug when compiled and run. Yeah.
So why did you get this test, or how did you come up with it?
So there was an update made in herd tools to change the semantics of an instruction, which gives rise to new behaviors. And I went, that instruction is emitted by an atomic. Let's see if there's a test that will exhibit a behavior that isn't allowed under the source model, but is exhibited by the compiled program. Kind of following on from that update to herds to match the architectural intent. Yeah, it's a bug. There's a similar one as well in the Linux kernel. There was a few years ago. It's been fixed. So the third point, and perhaps the most controversial one, we may need to revisit assumptions regarding the soundness of compiler optimizations with respect to hardware relaxations. So going back to this example again, the interesting thing about this is if you do put a int r1 equals and assign the value read by the exchange into P1, the compiler bug can actually disappear. The very act of constraining this program so that it keeps around that read will prevent the reordering of the exchange over the acquire fence. Now, if you compile this to target FOWM'8.2, the LLVM will emit currently a swap instruction. Now, the swap instruction, as according to the ARM, if its destination register is a 0 register, which is a special kind of register, WZR, XZR, it's not regarded as doing a read for the purposes of the DNB-LD barrier, which is what the acquire fence is compiled to. Now, as we see here, we have this DNB-LD, which is the acquire fence, and the destination register is the 0 register. And this is because the LLVM dead register optimization pass will rewrite the destination register of the swap to the 0 register because the read isn't used. This is perfectly valid, at least according to the C model and my understanding. Unused reads can be deleted, optimized away, who cares, fine. But in this case, this thread local optimization actually allows the reordering of the effects of this swap past the fence. So the conclusion I'm drawing here is actually this thread local optimization is actually affecting the concurrency semantics as a whole. Kind of surprising, you'd think. It doesn't directly affect Y, but it does affect the reordering of the effects of the swap. Now, this was a bit worrying to me. I looked back into the previous work on this, one of the papers on compiler testing with memory models. I found this claim that said, optimizations affecting only the thread local state cannot induce concurrency compiler bugs. Now, we have an example here that might question that claim. So the conclusion I draw from this is that we might need to revisit some of the assumptions regarding the soundness of these optimizations. This is a bit of a nasty bug, but nevertheless, it brings into question those kinds of assumptions. Yeah, so that's all I've got time for. To summarize, hardware implementations are getting more relaxed, and the implications of that are that we're going to need to parameterize our testing over models. We're going to need to have another look at our test generators to find more cases like this, and we may need to revisit the soundness of compiler optimizations in light of these relaxations. Yeah, I'm happy to talk about all of this stuff. It's a bit of a nasty bug. There's also some more open questions here. So, does the small scope hypothesis hold? Every compiler bug I've ever seen can be reduced to one of these tiny litmus tests, 4 lines of code, 2 threads, whatever. Now, in light of hardware relaxations, the question is there a large code, a bit of code that, when compiled, induces a compiler bug, but that code cannot otherwise be reduced to one of these tiny litmus tests? In light of hardware relaxations, there's more permitted behaviors of these machines, and therefore the question is, are there tests that cannot be reduced, or otherwise? Or otherwise, is there a proof that all programs can be reduced into these small examples? The implication of this is, in order to test in the large, we may need scalable techniques if we cannot otherwise reduce our programs. So that's where tools like Euler, D'Artagnan would come in versus Herd. Secondly, I implied that we might need to look at the soundness of optimizations. A follow-on question is, do we need to have another look at the C model? And equally, are there more examples like this? I can answer this one. It's yes. I know 2 of them. So there's the one I've reported, and there's also one regarding the semantics of atomic fetch add, which was highlighted by, I think, Will Deacon, gave the engineers in the kernel community a bit of a headache a few years ago, and then I believe that's been fixed in LLVM GCC 2. So, point stands, need systematic testing to see if there are any more nasty cases like this. Yeah, that's all I've got time for. Obviously, I want to thank my supervisors, James, Earl, and Lee, partner Anna, Richard, Wilco, and Thomas from ARM, Ali, John, and Tyler, who I've been working with recently, and all the people in the ARM architecture and compiler teams. I have to mention that I'm a student. My work is not officially endorsed by ARM, and this is my personal opinion. But yeah, I'm happy to talk about any of this stuff. It's pretty awesome. And yeah, thank you.
Thanks, Luke. Very interesting talk. So just in answer to your last questions about are there any more of these optimizations that are on SAND, I think there was a paper by Soham and Victor, this was back in 2015, they were mentioned a number of these optimizations that were incorrect, including Roach-Motel reordering and
Yes.
expression linearization and things like that.
Yeah, I'm familiar with Soham's work. I've read it quite a lot. So this is more with regards to sequential optimizations like this that do deletion of code. I'm happy to talk about that more. I'd need to think about it for a bit, but yeah, it's a valid question, I think.
Thank you.
Interesting bug. So in my work, I mostly focused on architecture-independent optimization, but it's interesting to see that it is also happening in architecture-dependent optimizations. So I have a question regarding where you show the reordering of the memory access. Exactly. So this ISHL DMB load barrier is still allowing this reordering of this.
Yep.
But according to, if I understand ARM semantics, then this should forbid this kind of reordering.
No. I can give you a litmus test you can run in under the ARM AR64 model. It will allow this reordering.
Okay, so I believe that. So the point is that is it a bug in the compiler or in the architecture in that
To be
case?
clear, it is a bug in the compiler. The compiler, by rewriting the destination register to the 0 register, has triggered this edge case that allows reordering. The architecture implementation and the model, they don't have bugs. This has been in the ARM for years. If you look at the ARM pseudocode and you trace the swap instruction, this is in there. This isn't a bug in the architecture. This is just the compiler mapping and trying to delete something that you might reasonably think you don't need, but in this case you do.
I mean, it's a choice in the architecture. You might wonder if they should have done it that way.
It's an architectural oddity. I mean, what does it mean for a store to have acquire semantics? It's a bit weird, right? But
I mean, the fact that you can just say, we're not going to treat this atomic as a load because it's going to this one register.
yeah,
As
but
an
it's
ISA architect and hardware coordinator, that
yeah.
rubs me really funny.
Yeah. Yeah.
So if I'm not wrong, you have mostly considered C11 or RC11 as the source language. Have you taken a look to LKMM? Because a few weeks ago I was talking with Paul actually, and I was telling him that our tool can do some kind of like compilation, but we're kind of like hard coding this. We're not handling the real assembly that is there. And he was asking me, did you find any bug in there? And I say no, and one of the reasons why I think we did not do this is because while for LKMM there are many litmus tests, there are like 5,000 around there, like they don't really exercise like most of the, for example, read modify instructions. I think like only a handful of test cases have this. So
Yep.
I think that could be a situation where you could find something, particularly because if I'm not wrong, I think that the inline assembly of RISC in the kernel has been rewritten quite recently. So maybe that's a good target.
Absolutely, yeah. So I focused on C and C++ initially. RC11 is, the Linux kernel is a target for sure. The small scope hypothesis holds. Can we compile a large fragment of the Linux kernel and feasibly get all of the outcomes in an amount of time that is acceptable to run in CI, right? Yeah, or can we reduce these tests down to something a bit more feasible?
So I'm very happy to see more compiler testing, which has always seemed a very hard thing to do. My intuition is that there are any number of unfound bugs that need larger test cases. And I mean, more broadly, these litmus tests that we're used to using, they're essentially tests of the semantics. And it's only by lucky accident and some aggressive test harnesses that they turn out to be useful for testing hardware. And for making things that will trigger interesting compiler optimization failures and interactions between those and the architecture models, we need some much fancier generation of interesting LLVM for particular passes or interesting C, which is a hard problem, but a quite important problem.
Absolutely.
Someone
yeah.
should do that. Maybe
Absolutely.
lots of people should do that.
Yeah, I know John and Ali and Matt Windsor, they did the C4 tool that takes one of these tiny tests and fills it with a bunch of code. The metamorphic test, they turn a small litmus test into a pretty massive one actually. It could be useful to throw that through the compiler, see what comes out. I've had a look at that, but I haven't made any progress on that just yet. I agree though, I would love to see a counterexample of one of these large tests that induces a bug that we can't otherwise reduce to these tiny litmus tests, right? Because it's a question of reducibility as well. Like, does C reduce? Can we use C reduce for concurrent programs, and so on? Because engineers, they won't read a 400-line bug report. They'll read a 4-line bug report and go, oh, this is allowed, this is forbidden, this is a bug. Well, let's fix it. You know, it's a convenience thing as well as a question of reducibility.
Yeah, my inclination would be to try to do this per phase if one can, because the end-to-end problem is
Huge, yeah.
kind of yucky. But
Just a quick question, since you told us you read the pseudocode, is it the case in that case that this line is directly implemented in the pseudocode as the swap, just not doing any read?
Yep.
Okay.
It's the same for LDAD STAD,
Yeah.
which is the target of atomic fetch add. It's one of those two instructions. Same thing.
Okay.
Do you have the bug number for LLVM
Yeah, I can give you the bug report.
I can ask in the break if it's
Yeah,
easier.
if you go to my CGO paper, shameless plug,
Okay, yeah, I can do
it's
that.
the running example in there.
Great, perfect,
And,
thank you.
Yeah.
I just want to let you know one interesting compiler bugs, important compiler bugs we recently found. The flow-sensitive escape analysis is wrong. So basically, compiler assume that until your local variable's address is escaped, but up to the first point where it is escaped, until that point, the compiler assumes that it's a local. No one can, so you can do constant propagation or whatever, but that's wrong. Because the escape point can be reordered earlier. So we constructed a county example and we ran it on ARM machines and actually observed the miscompilation. So we reported and then they accepted it as a bug, but somehow anyway we have the bug number LLVM and maybe both GCC and LLVM. But anyway, so just conceptually flow sensitive escape analysis, we think it's maybe sequentially thinking that it's correct, but actually it's incorrect.
That's very interesting. Let's chat later, yeah? Thank you.